In this video, we're going to go over heating and cooling curves, which will show us how to get from one state of matter to another. So heating, cooling curves. And they're the same thing. One is just backwards. So we'll be doing basically just heating curves. And we kind of know from experience that to get from a solid to a liquid to a gas, we have to add energy. Right? So if you want to melt ice or boil water, right, you've got to add energy. And so there's a graph that can actually kind of show us a lot of how this happens. So on the y-axis we'll have temperature. On the x-axis we'll have something similar like the amount of energy added or something like that. And the basic shape of the graph will look like this. And I'll label some points here. I'll label where we first start off S for the start point. Then we have A, B, C, D, and E. And from the starting point to A, we see that this is actually a solid. And as we add energy, the temperature increases. So added energy goes to increased temperature, which means, remember, increased kinetic energy, because temperature is just the average kinetic energy. And that kind of just makes sense. We added energy, so the solid got hotter. And we can look in particular at the slope, right? So if I were just to blow part of this up, just looking at the slope, if we have energy here on the bottom and temperature here on the y-axis, the slope of this line is related to this specific heat, right? So if we need a lot of energy to make the temperature increase by a little bit, so I'll exaggerate. So how about this? We need a lot of energy, right? We need 3 units of energy for the temperature to go up by 1 unit. That means that it needs a lot of energy just to increase in temperature, and that's a high specific heat. Remember, C is the kind of abbreviation for specific heat, which has units of joules per gram degree Celsius. And if it takes very little energy, maybe just 1 unit of energy to go up 3 degrees Celsius, then that would be a very low C, which would have a really steep slope. Okay, and so that kind of takes us through something that seems very normal to us. The next part is kind of weird, and that's from A to B. From A to B, we're still adding energy. Notice that. We're still adding a good amount of energy, but the temperature is not increasing. So at this point, the solid is starting to melt. So solid is melting into liquid. And the energy that we add, you see, is not increasing the temperature, so it's not increasing the kinetic energy. So the energy must be going to the potential energy. And remember that solids have very negative potential energies, and liquids, while having negative potential energies, don't have as negative of a potential energy. So what we're doing is we're increasing the potential energy of the solids until it gets to the level to make it a liquid. Another way to think about this is that there's only a certain maximum velocity that solid molecules or atoms can move while still being a solid. And you might want to think about that if this makes sense to you. Again, in our kind of ball and spring model, they can only move so fast. As a solid, because they're all connected to each other, so they can only go so fast. And so when they're moving at their top speed, which is this temperature here, which is called the melting point, right? That's the fastest they can go. It's the highest kinetic energy they can have. If you add more energy, it goes into breaking down the crystalline structure. It makes them go from a solid to a liquid. And only after that can the kinetic energy increase again. In the next video, we'll talk about B, C, D, and E.